Now we start the problem 64 of your textbook. It says, suppose the rod with the balls A and B of the problem 63. Now, what is problem 63? If in case you have forgotten what is problem 63, problem 63 was like this. There are only two balls A and B, both of mass M, connected by a light rod of length L. So this rod of problem 63, this rod of problem 63 is now clamped at the center in such a way that it can freely rotate about its horizontal axis through the clamp. That means now the ball is, two balls are kept like this. Two balls are kept like this now. This is A, this is B, both of mass M, here also mass M, connected by a light rod of length L, and it is pivoted at the center. Now, it says, the system is kept at rest in the horizontal position. So somehow the system is kept at rest here. Somebody is holding it so that it doesn't start rotating. Then what happens? A particle P of same mass M is dropped from a height h on the ball B. The particle collides with B and sticks to it. That means a particle P of same mass M was at a height h. It drops from here and then sticks to it. The second, this is number one position. And number two position is, this is B, this is A, and P sticks to it. This is the fulcrum. The question is, find angular momentum and angular speed of the system just after collision. Now, we start this way. So this was position, this was situation 2. There will be situation 3, 4. We shall do it later on. Let's solve the first part, A. Find the angular momentum of the system that they want to find out. Then, what is the velocity of P when it drops from the height h? We start from here. Velocity of P when it drops from height h. We know from the kinematics chapter, it is under root 2gh. This is the velocity of P. And so, what is the momentum of P? So, momentum of P just before collision, is mass multiplied by this velocity, that is m under root gh, m under root 2gh. And this momentum of P creates the angular momentum. And we know angular momentum is this linear momentum of the force multiplied by the distance from the axis, which is L by 2. Total length was L. So, angular momentum of the system. So, angular momentum of the system is equal to the linear momentum m under root 2g h multiplied by the distance L by 2. This is equal to ml under root 2gh divided by, if I write root 2 here, then I remove 2 from here. Then it will be ml under root gh, ml under root gh divided by root. Okay? ml under root gh divided by root 2. This is one thing. This is the angular momentum of the system. What is the angular speed of the system? Now we have already understood, already you have learned it number of times. From angular momentum, we can find out angular speed by the equation L, angular momentum L equal to I omega, right? So we need I, moment of inertia. So I, or moment of inertia, I, which is moment of inertia of the system, I, or moment of inertia of the system, is in one end we have mass m, and one end we have mass 2m. So 2m into L by 2 whole square plus m into L by 2 whole square. mr square plus mr square is equal to 3m into L square by 4. 3m L square by 4. Now we use the equation I omega is equal to L, moment of inertia. From here we get omega is equal to L upon I. From here we get L, we have already found moment of inertia, ml under root gh by root 2. So this is ml under root gh by root 2 divided by moment of inertia 4 will go upward 3 ml square. This is equal to root, if you cross root 2 and 4, you have got root 8 here. M and M get cancelled, and L gets cancelled with L square, leaves only one L. So we have under root 8GH by 3L. So under root 8GH by L. So this is our second answer. Then part 2 of the system question is really interesting. Really interesting. What it says, what should be the minimum value of H, this minimum value of H, so that the system makes a full rotation after the collision? Here, you have to really perceive the system behavior, how the system will behave. To start with, this angular velocity will of course create an angular momentum. Will of course create a kinetic energy. Let us find out this kinetic energy. Part D. Angular kinetic energy is, or rather we say rotational kinetic energy, is half I omega square. Is half I omega square is equal to half I, we have already found, moment of inertia We have already found 3 ml square. Moment of inertia we have found here. 3 ml square by 4. 3 ml square by 4 multiplied by omega square. Omega was under root 8 gh by 3l. So it will be 8 gh by 9l square. Now 2 and 4 gets cancelled with 8. Right? 3 cancels with 9, leaves a 3 here. And L square and L square cancels. So what we are left with mgh by 3. This is equal to mgh by 3. Now the interesting part starts. Look at the system. Does it need a kinetic energy to make 90-degree rotation? That means when A comes upward and B and B and P are here. B and P are here. Earlier it was like this. B and P was here and A was here. It has rotated by pi by 2. It has rotated by pi by 2. Look at this. Here I have mass m. Here I have mass 2m. So, just due to potential energy, this will take a 90-degree rotation. This is very obvious if you look at the system. If you have a small pencil and one end is heavier, if you leave the pencil to rotate, obviously the heavier part will come down. For this, it does not need any kinetic energy. It drops here just because of its potential energy or due to gravitation, right? So this is the catch of this problem, of this particular problem. Here, we write, this is this is condition 2, we say this is condition 3. So we write, the system does not need any kinetic energy rotate by 90 degrees. It will rotate 90 degrees due to its potential energy. It will rotate 90 degrees clockwise as shown in picture 3 by its potential energy. Because potential energy of this 2m is much higher than the potential energy of the only one mass m. So we analyze this part of the rotation. During this 90-degree rotation, we write, during this 90-degree rotation, A goes upward. So A gains potential energy. A gains potential energy by how much? M, G, and L by 2. And B plus P loses potential energy. Loses potential energy by how much? 2m g L by 2. So A gains potential energy mgl by 2 and other end loses potential energy double of that. So there is a net loss of potential energy. So there is a net loss of potential energy. How much is that loss of potential energy? Loss of potential energy. Loss of potential energy during this 90-degree rotation is equal to mg 2 mg L by 2 minus mg L by 2. 2 mg L by 2 minus mg L by 2, which is equal to mg L by 2. This loss of potential energy, where does it go? This potential energy gets into the kinetic energy of the system. It creates additional kinetic energy. This creates additional kinetic energy. So, total kinetic energy after 90-degree rotation it already had a kinetic energy mgh by 3 that happened when the ball P dropped on B and stuck to it. So now it is mgh by 3 plus additional kinetic energy of mgl by 2 has been created because of this 90-degree rotation. Right? Now, look at the system once again. That's why I said this question is very interesting. This is the situation 3. Now, at this situation 3, if it has no energy left, then obviously the dumbbell will rest in this condition. The heavier part will hang downward and the lighter part will go upward. But it has a kinetic energy. With this kinetic energy, it will try to keep rotating. And with that kinetic energy, if it can rotate by a complete 90 degree, depends upon how much kinetic energy it has. If it can rotate by complete 90 degree, where it has a mass 2m upward and m downward, and this we call m downward, and this we call situation 4. If it can completely rotate, that means from situation 3 to situation 4, it just travels the total 180 degree and the situation of the 3 balls becomes opposite. If it can do, then what will happen? Thereafter, what will happen? It is not asked in the question, but you need to know. If it can go in the situation 4, then once again, due to potential energy, this end will start coming down. And finally, it will at least come to this condition. It will at least come to this condition. and further. And if it comes to this condition, then you see the rod has taken a complete 180, complete 360-degree turn because it has asked that it makes a full rotation. So we have to now only find out whether the system can make from here to make another 180-degree turn with the kinetic energy which is left with it, right? So if it has to take another 180-degree turn, right? So we do, if it is, this is here, if so, this is the total kinetic energy it has in its pocket now. Now, if it has to take another 180-degree turn, if it takes another 180-degree turn, then once again, one end will gain kinetic potential energy, another end will lose potential energy. What is the gain and loss? Let's see the picture here. From here to here, from situation 3 to 4, the B and P together, 2m, will gain potential energy due to a height L. And the mass A will lose potential energy due to a drop by a height L. So if it has to take another 180-degree turn, then what happens? The gain in potential energy let me write here within bracket by B and P is equal to 2mgl, and loss of potential energy by A is equal to mgl, is mgl. So what is the net gain? So net gain in potential energy required is 2 mgl minus mgl is equal to mgl. Now we have to see whether this amount of kinetic energy can provide this amount of potential energy. If it can provide, then it will take a full 180-degree turn. Otherwise, it may take a turn of less than 180 degree. Again, the heavier end will drop to the bottom. So we equate these two. So to make a 180-degree turn, these two will be same. That means mgh by 3 plus mgl by 2 will be equal to potential energy mgl. This was the kinetic energy, and this is the potential energy required. So from here we get mgh by 3 is equal to mgl by 2 minus mgl by 2 is mgl by 2. From here, m and g gets cancelled. What we are left with? So h is equal to 3l by 2. That means, coming to the problem, If this height h is at least 3L by 2, then it will take 90-degree turn due to gravity, and then it will take another 180-degree turn due to kinetic energy. And if it can come to this position, then it will, of course, take at least another 90-degree turn to come make a complete full rotation. So that was the problem, right? We shall take the next problem now.